Hello, I'm Gérard Medioni. I'm a Vice President, Distinguished Scientist at Amazon. I'm also an Emeritus Professor at USC, and what I want to share with you today is my personal journey of more than 40 years in the computer vision field. So, with that introduction, let's start. I'm going to do it in 3 chapters. We'll start with the academic part, then with the startups, and then with my current position, which is at Amazon. And those are not quite sequential because my academic life and my involvement with startups are overlapping. So let's start. It's important to kind of give you, first of all, a brief timeline. I talked about 40 years at US, 40 years. Well, it has been 40 years at USC. I'm inbred in the sense that I was a student at USC, then I became a professor, and I became chair of the computer science department, and then I became emeritus in 2019. So just to give you this timeline approximately, since 1979 is when I came from France to the US, graduated in 1983, and then you see this timeline right there. And you can find a lot of my work through my papers during that time. What is less known is the non-academic part, which is a chapter 2, which is started pretty much early, 1984, and with a number of companies. And the reason I was involved with this, most of them are startups, is because I'm not the ivory tower type of professor, where you invent a problem, then you solve it, and then you ask if anybody cares, but instead going to companies and finding interesting problems that are not solved because there is a core science problem to be solved. So let's start. Chapter 1, USC. Just to give you a little bit of context here, computer vision is a young field. It started in the 1960s. One of the early person was at MIT, and Larry Roberts, is the person who really created the first computer vision papers. If you look for Larry Roberts, by the way, you're not going to find much about his computer vision except his thesis. He went on to really be one of the founders of the internet, at the time called the ARPANET. Okay, so being in a field in the early days is very exciting. Why is it exciting? Because you don't know what you don't know. So it presents both a set of opportunities and, of course, a set of challenges. And I'll talk about some of them, but it has to do with, well, how do you get the data to start with? Second, you're not working in a silo, isolated in your lab. You need to communicate and compare the results, and you need to ask the question, how fast can we solve these problems? And you face this explorer's dilemma, which is you don't even know what problems need to be solved. And you find a problem, you say, well, I should work on it. Then you should ask the question, is it a relevant problem? And what are the potential solutions? And finally, when you have enough maturity into the solution, you want to ask, well, how can we transition this to real world applications? So let's talk about the data. I was fortunate to have joined the USC Image Processing Institute. This was where all the data at the time, this is where it originated. You're probably familiar with Lena, which is the picture on the right, which was used by everybody in the early days to test algorithm. So how did we get the image in the first place? This image comes from a magazine, and there was no easy way to capture the image except by scanning it. How do you do it? You use a drum image scanner, which means you put the image on a cylinder, and then it is being scanned by a point scanner. For every point, you get a RGB value. This is a very long and painful process. It takes closer to an hour to get a decent picture out. So let's say you have an image. How do you share it with anybody? Well, you have a file. You need to figure out what it is. There was no standard header. There was nothing like that. So for example, if you get a 65,664 byte, that means it's probably a 256 by 256 image with a 128 header. And you look at it, and if it's noise, then you say, well, maybe it was a 512 by 128 instead. The other thing you need to realize with this data is that you need to store it somewhere, and it's very, very, very expensive. The storage at the time in 1980 for 1 gigabyte was $40,000. So the entry barrier to get into the field of computer vision was very high. In fact, many of the papers that you see from the early days, for example, detection of tanks or recognition of tanks, works on 16 by 16 images because that's all you could fit in memory. Well, let's compare it to what's happening today. Today, we get 300 million photos that get uploaded every day. We get 300 hours of video uploaded to YouTube every minute. So we went from a scarcity of data to a deluge of data. So data is no longer really a problem today. And let's talk about this scientific communication and progress. Well, the way it worked in the early days is that everybody got their data set. You want to work on something? Well, you manage to get one picture, two images, maybe, and then you write a paper. Well, you get a call. Can I have your code so that I can replicate? You say, well, yes, of course, I'll be happy to give it to you. What language are you using? Well, I'm using Lisp. Oh, I'm using Fortran. Oh, well, that's going to be a problem. What library? Well, we don't have libraries. We don't have interfaces. So the communication was going through conferences and journals. And that means that the progress is fairly slow because it takes 1 to 2 years for a paper from submission to publication. So very slow progress. It's instructive to look at what's happening today. Today, we have annotated data sets available for everybody. We get papers on archive, and they get updated every day. Every day you have something new. And you have code on GitHub. So you can directly download and try and see and replicate the results. So the progress, instead of occurring on a 6 months or yearly basis, is now occurring on a weekly basis. All right, I talked about the explorer dilemma. So what is that? So I give you an image and you say, I want to know what it is. Well, what blocks do we build? What are the key components? One of them is you say, well, how does a human visual system work? And I know there is a neurons that are very sensitive to edges. So we extract features. We have to find edges in images. Well, yes, I did some. So you have the similar thing. Instead of edges, you could try to do region segmentation. Once you have these features, you need to group them. And you do that by linking, merging, fitting. And again, I did some of this work, and tensor voting is some of my papers in this field. Then you have high-level reasoning, which is not just talk about features and groups of features, but go all the way to object recognition or 3D pose estimation. And again, in the early fields, we did everything. So I did that. One other thing you can ask is, why do I need to stop at one image? Maybe if I use two images, I can do better. And then you say, well, we have two eyes, we can do stereo. Obviously, with two images, it should be easier. Or you can say, well, we don't process one image, we get an image sequence. So you get this motion analysis. And again, that's another direction in which we can go, which is image sequence analysis. So if you start building those blocks, you can start building solutions to real problems. There is another direction, which is to say, well, we don't have to necessarily replicate the human visual system and do what people do. Maybe we can simplify the problem. Maybe we can restrict the domain, or we can use depth. So instead of having a regular camera, we can have a depth camera. So let me show you some examples of these ideas. So the first one is going to be, well, what if I have, instead of a regular camera, RGB camera, I have a camera that gives us depth. So, and the rationale behind that is, if trying to get 3D from one image is so hard, why not start with 3D? So I built some early blocks to do that, including ICP, the iterative closest point in 1992, which happened to be my most cited paper. And what it does is, given two clouds of points, how do you align them? And that's a fundamental problem in there. So in the simplification, or in there, you see that the application only appears decades later. So for example, this was in 1992. Well, in 2007, the Defense Advanced Research Project Agency, DARPA, created a program called URGENT, which is Urban Reasoning and Geospatial Exploration Technology, which the goal was to find all the components in a range image. Find the roofs, find the chimneys, find the wires, find all of these in there. Another advance was in 2010, the Microsoft Kinect came, and it was a revolution as it offered a $100 consumer product. And I'll talk about it later because I was involved in some of it. Another example, you have all seen the famous game Where in the World is Carmen Sandiego? So what is it? Well, imagine that you're dropped off, you look around, take pictures, and you need to answer the question, where in the world are you? So, that's one of the cases where you invent a problem. So in 1995, we published with Fritz Stein a map-based localization using the panoramic horizon. That is, you look around, you extract the horizon line, and you say, if I have this horizon line, it's actually unique, and I can tell you where this picture was taken from. It didn't get a great reception at the time. The comments were, why do you want to solve this problem? It's useless. Just use GPS and you have your solution. I had a good answer to that when I said, well, what if you go on Mars? You won't have GPS on Mars, so you still need to solve the problem. Regardless, so 2011, the IARPA created the Finder program. And what was the Finder program is, I give you an image or a set of images, and you're supposed to tell me where in the world you were, which is exactly this geolocation task. Of course, at that time, I got a number of calls. Hey, we have this, we have read your paper, and now we need to actually put it in practice. So my citations shot up at that time. Okay, so those are just two examples of the type of application we have. I want to talk about the next one right here, which is a picture of me here wearing the device we created, which is simply a camera. It's just a camera right there. And what we wanted to do is produce visual aid for the blind. Why did we do this? Well, because the tool were starting to become mature. And this is a significant social impact to provide navigation aid for the blind, indoors, both indoors and outdoors, performing planning and obstacle avoidance. So we went to the Braille Institute in Los Angeles, and we did a proof of concept. We had this vest that you can see there. And the vest had 4 little motors. So whenever there is an obstacle in front of you, all 4 motors would buzz and the person would stop. And then if the left motor buzzed, that means you should turn left. If the right motor buzzed, you need to turn right. And the feedback from the users was outstanding. This was great. But it was still a long way to a product. In fact, I got a call from a blind user, and she said to me, you know, when can I buy it? This is wonderful. I need it. When can I buy it? And that's when I realized, you know, this is not the role of academic research. This is not what we are supposed to be doing in academia. We need to interact with industry, and we need to find a different channel to go from this prototype to a product. So I'm going to move now to chapter 2, which is exactly the motivation for this, which is how do you interact with industry and what do you learn? And not all lessons learned have to do with technology, as you will see. So I gave you the chapter 1, which is a USC and the academic life. Let's talk now about the chapter 2, which is our startups. So as I told you, I engage with industry outside of academia very early in the career. And I will choose some of these. I'll talk about OptiCopy, I'll talk about APSIS, and the lesson that I learned. I'll talk about geometrics, big stage, lesson, PrimeSense. And then in the third chapter, we'll talk about Invention at Amazon. So let's start with the key point here. The point of disruptive technology is you can look at it 2 ways. One, I mean, the good news is that it's disruptive. The bad news is that it is disruptive. So what does that mean? The good news is that it opens road to new opportunities, but because it doesn't fit to existing models, it's very hard to just take it and put it in existing frameworks. So it creates these hurdles to adoptions. So I'm going to show you a number of examples of that. Let's start with OptiCopy. OptiCopy is addressing an interesting problem, which is the automatic registration of half-tone separations. So give you a little context here. The company was making state-of-the-art pre-press equipment, and they wanted to automate this automatic registration. They tried a solution that didn't work at the accuracy which was required, and then they asked me for help. And I was a fresh assistant professor, and naive as I was, I said, of course I can do it. And so let me tell you what the problem is. What is a halftone to start with? Well, if you start with film, film is essentially continuous. I mean, you can see it here. When you want to go to print, you transform the intensity of the, and let's go with a gray tone for now. you encode the intensity by the size of the dot. So if the size of the dot is 0, then it's white, and if the side of the dot is full, then it is black. So that's how you go from one to the other. And here's an example on the screen of different resolution of the dot size. Okay, so that's for black and white. Well, how do we do color? Well, we do color by using 4 different screens, and each screen encodes a different color component: cyan, magenta, yellow, and black. You may want to ask, why are we using 4 colors instead of 3? We know that the human eye is using 3 sensors, so why would we be using 4? And the answer is very simple, is that black ink is cheaper than color ink. Therefore, you're trying to cut the cost by using as much as possible of the black. So notice that as this screens align, the eye is blending those colored dots to create the illusion of a uniform color. So if you want to get cyan, you get this example right there. If you want to get green, it's what it shows there. Okay, so the process is straightforward. You start with a color image. You create films, 4 different films, which encode the content in each of these bands. So you can see right here, what I'm explaining is on the top is the continuous version, and the bottom is the digital one. So you could take from 1 color film, you go to 4 film. The content is obviously different because you have different content of red, green, and blue in there. And when you align them, you need a few microns accuracy. So I'm not going to tell you how we did it, but essentially we achieved great success from a technology point of view. We were able to register 10 sets an hour versus 4 for humans, and we were more accurate than humans. So great tech achievement, and it was actually a very good business achievement, because given this technology, the whole company was sold in 1987 to Polychrome, and it was really based on that technology. So it was a successful exit. So we have a tech success, we have a business success. Question is, so what? And the answer is, by the time it was ready for adoption, the industry switched to digital, making the technology completely obsolete. So again, why? Because when you're doing a digital separation, you are by design preserving the registration. So if you go into Photoshop and you say, give me a separation CMY black, you get it, it's automatically registered. You don't need the technology that I developed. Okay, what is the lesson here? This is the first lesson. It's an important one. You need to keep aware of the global context and anticipate the disruptive changes which may disrupt your disruptive technology. Knowing your current competitive landscape is not enough. So just knowing who your competitors are is not enough. You need to project advances in the field. All right, lesson number 1. Let's go to the second example, which was EPSIS. It's a real-time technology to insert computer-actuated content into a video. It needs to be absolutely seamless. Used for virtual advertising, it can use for sports enhancement, telling you what the distance to the goal is. It could be used live, it could be used in post-production. So rather than give it to you, here's the example. So what you see here is 3 different broadcasts, whereas the ads on the side are different. We have replaced here, in the live video stream, we can replace the ads accordingly. So this is a very exciting technology if you think about it. It is nothing but the ancestor of the 10-yard yellow line that you see in American football today. That's what it is. So great technology, needed to solve some really interesting problem in panorama, feature tracking, object detection, image mapping, lighting, augmented reality. It's a hard problem, a real-time constraint. You need to start replacing those billboards even when they are at the edge of the field of view. You cannot have any jitter, and of course, you need to worry about occlusion. So it worked. Surprisingly enough, for some people, the technology worked actually very well. We deployed it for several high-profile sports events. I remember I was at an event in the south of France for a Formula One, and I could see the real image, and I could see the replaced image. It was very exciting. It had the potential for a huge business opportunity. I mean, the word from the company we were working with at the time was, we're going to make hundreds of millions of dollars with this. And the dollars, of course, are from the advertisers. Well, guess what? 3 companies failed trying to do this. It's surprising. So you want to ask, well, why? Why did it fail? I mean, you have the technology that works. You have a market segment that should be attracted to it. So why is it? First one is, well, how do you price it? You know, when you sell a billboard, you say, I'm paying you for the billboard. Here you pay for what? Minutes on the screen? How can you guarantee that you have that many minutes on the screen? The other one is, well, how do you insert it in the chain? Where do you go? Where do you get the input to start with? So here's the way it worked, is that you go to the primary broadcaster who is on premise, and you say, I need to get access to your tube right there. And they say, sure. And they takes a handout, and you're going to pay for it. Then you go to the secondary broadcaster and you said, hey, you need to broadcast my feed. And they said, no, I don't have to broadcast your feed. I can broadcast the original feed. And you say, okay, here, I'll pay you some. Then the league says, wait a second, this is a league game. You can't do that. And you say, sure, put your hand out, I'll give you something. Then the teams say, hey, wait a second, we are the actors in here. We are on the stage. And you say, sure, put your hand out. And then you have the stadiums that says, oh, wait a second, when I sell a advertising panel, I get money. And you say, of course, put your hand out. And at the end, you know, it's a very long chain of handouts that you have to do along the way. Way too many parties to the deal. So who made money in all of this is the people who actually put the deal together. So where is it today? Well, today it's mostly used in post-processing, just like slow motion. And the money from advertisers, no, really didn't make it. So we have here an example of technologies that succeed, but again, technology without a business model is doomed from the start. You need to proceed in parallel. Every time I ask the question, what is the business model? The answer was, don't worry, we're going to make hundreds of millions of dollars. Well, guess what? Didn't happen. So that was the second lesson. So let's fast forward a few years and let's talk about big stage. At USC, I had created a way to create a very, very accurate face model from images. So a company came and said, we know how to leverage that. We're going to upload 1 or 2 or 3 pictures, and then we're going to create this virtual, we can create personalized ads, personalized cards, personalized videos. And this was great idea. Hey, I can actually replace an actor into a video clip. Wow. It sounds what we call today deepfake. Well, this is the ancestor of deepfake, where you actually put a new face onto an existing one. So there were some very interesting problems. How do you deal with expression changes, high movement, and so on? So what you can do is you take a video clip, you can prepare it, and you, with one click, you can insert yourself into it. We did it. I'm going to show you one example, but we did it. If you go to that YouTube link, which is right there, we did it with a Michael Jackson Thriller, a very short video clip where people became Michael Jackson. And in 1 week, with no advertisement, nothing, we got 3,000 people who became Michael Jackson, who replaced Michael Jackson in Thriller. Let me show you what we did with Professor George Becky, was a professor at USC. It was his 75th birthday and a roast. And what I did here is I took this one picture and I put George in the movie. So here it is.
He's shot me like he's lost a lot of blood, Doctor. Attaboy, Murdoch!
Really have to lighten up on this paranoia. They play dirty.
And we play dirty.
Oh, brother.
I love it when a plan comes together.
All right, so you saw what it is. It is not movie quality, but it is YouTube quality. So this was the example. So again, interesting story. So it worked again, but the company was raising a B round in 2008. Remember 2008, the financial crisis? Well, the company ran out of money. And really, the company never had a business plan articulated. It was the same story. Whenever I asked, what is a business plan? They said, don't worry, we're going to make lots of money. Well, didn't happen. So the other thing it tried to do is it tried to monetize by taking small projects. It tried to monetize the technology before finishing the product. And that actually prevented the product from being finished. So the third lesson is that you need to stay focused. You can't just try to do other things while you're not finishing the product. So focus is essential. But lesson 4 is probably very, very actionable. A product is miles away from a prototype. So do not try to sell a prototype. Finish the product, and then you can sell it. But there is one more lesson, which is timing is a predominant factor for success. In fact, there was a study by the Harvard Business School that listed all the potential factors and correlated that to success or failure of startups. And timing is a #1 factor. The bad news is that most of the time, a startup does not have any any control or very little control over timing. Okay, let's move on to PrimeSense. As I was presenting that, one of my colleagues said, after all this failure, somebody is still willing to hire you? Well, I guess the answer is yes. So PrimeSense, what is PrimeSense? PrimeSense decided to create a consumer-grade 3D image capture for under $100. And the idea was to use a body as a user interface, mostly for gaming application. This was a very disruptive success. It revolutionized several fields, including robotics. Within 6 months of the introduction, 1/3 of the papers in the robotics conference were talking about using this device as input. So what does it look like? Well, here it is. On the top left, what you have is the image of the prime sensor. What does it do? Well, it works on the principle of triangulation. You have an infrared light source, which is encoding, which has an encoding on it. And then you have a processor and a sensor, so you are projecting a invisible IR light. And by doing this triangulation, you are creating the depth image, which is on the right over there. We also had a regular RGB camera, which gave you the image right here on the left. So you have the emitter, the receiver, processor that gives you this image right there. Now, when you have that, you can fit an articulated model to the people and create an avatar in motion, which is accurate, and you can use it for games. You can hit a ball, you can catch, you can box, you can do all this gaming processes. So we built it. It was a great success. Microsoft was a major customer which uses it in the Kinect One. And according to the Guinness World Records book, it is, even till today, it is the world's fastest selling consumer electronic device ever, moving more than 10 million systems by March. That means that every day we were selling 133,000 units from November to January. This was a mega hit, and the company was doing absolutely great at the time. But there was a setback. Again, there was a number of reasons. Microsoft wanted to have their own solution as opposed to a single supplier. So in 2012, we laid off some of the employees, and we tried to attempt to reinvent the company instead of just saying, well, let's just keep on improving the technology. So we came up with a low footprint design, which is the Capri. So if you want to see what the white one right here is the original proof of concept. This is the prime sensor, and this one was a reduced size one that we came up with. That's a Capri. Well, it was a successful exit. The company was sold to Apple in December 2013 for $330 million. And if you have an iPhone, and if you look at the top of the iPhone, the camera on it is on the iPhone 10, it is a prime sensor. So that is the success of it. So this time, instead of giving you lessons of what not to do, I'll tell you the lessons of what to do. So the key was you need to have a bold vision. You need to think big. It was a high-risk proposition. There was only 3 possible customers, and 2 of them said no, and the third one said yes. So it was a very high risk proposition. The company had a very strong leadership, both technically and on the business side. And it never deviated from the business model, which is we need to sell the processor and license the manufacturing. That's it. Of course, we also needed the ability to adapt to ambiguity and to change. So we knew what the end goal was, but we were willing to adapt as we went. So those are the lesson here. And that takes me to the third chapter, which is Amazon. So it has to do with invention. So I was approached, at the time, I was approached by Amazon to work on something which was secret, which was a revolutionary. So that made it very attractive to me, of course. And what is it? What is this notion of invention on behalf of customers at Amazon? It comes from the very core of the company, which is captured in this Jeff Bezos quote. It's not customer job to invent for themselves. It is your job to invent on their behalf. You need to listen to customer. They won't tell you everything. Therefore, you need to invent on their behalf. And I'm going to try to give you two examples of that notion, of that principle right there. The first one has to go with Amazon Go. This is what we call the just walk out technology. So for those of you who are not familiar with it, let me show you the promo video, the short promo video we had at the time where it was unveiled.
4 years ago, we started to wonder, what would shopping look like if you could walk into a store, grab what you want, and just go? What if we could weave the most advanced machine learning, computer vision, and AI into the very fabric of a store so you never have to wait in line? No lines, no checkouts, no registers. Welcome to Amazon Go. Use the Amazon Go app to enter. Then put away your phone and start shopping. It's really that simple. Take whatever you like. Anything you pick up is automatically added to your virtual cart. If you change your mind about that cupcake, just put it back. Our technology will update your virtual cart automatically. So, how does it work? We used computer vision, deep learning algorithms, and sensor fusion, much like you'd find in self-driving cars. We call it Just Walk Out technology. Once you've got everything you want, you can just go. When you leave, our Just Walk Out technology adds up your virtual cart and charges your Amazon account. Your receipt is sent straight to the app, and you can keep going. Amazon Go. No lines, no checkout. No, seriously.
All right, so why did we build Amazon Go? What is the customer problems that we're trying to address here? The customer problem we're trying to address here is that we believe no one likes waiting in line. There have been a number of innovation in brick and mortar retail over the years. I mean, you can think of credit cards, you can talk about barcode scanning, self-checkout station, but fundamentally, the customer experience is still the same. You shop, then you wait in line to check out. Then you pay, then you leave. With this, with Amazon Go, with Just Walk Out technology, we're changing the experience. As you saw, you use the app to enter the store, you take whatever you want, and you just go. no lines, no checkouts. You just walk out. Okay, so it's a fairly simple equation to solve. I mean, what do we have to solve? You need to solve who took what. So, so what makes this so complicated? What makes it so complicated is a complexity of the real world. Let me just show you what's really happening. So we have cameras, we have fixtures, we need to send the data from these cameras and fixtures, and we do it through streaming services, and we build this just walk out technology that answers the question, who took what? So for every item that's being taken, we answer the question, who took what? As a result of it, we need now to know who and what account to charge. Well, we do that at the gate. The gate, the QR code provides a payment method. And then by adding all the individual events, we create a virtual shopping carts, put it together, create a customer cart, and then we can issue a receipt. So let me talk about this just walk technology for a little bit. What is the component? What is this? Well, turns out I probably could write a textbook, a computer vision textbook, using just walk out as a use case. So what is it? Well, first of all, you have cameras, and we need to know where they are with respect to the rest of the store, and where they are with respect to each other. And that's what we call calibration. Now, we need to answer the question who. So to do that, we need to detect people, customers. So that's the role of person detection. Of course, we need to know what, and that is the object recognition, which is a very mature field in computer vision. In order to associate the item to the customer, we need pose estimation. And finally, we need to know what happened. So what is it? Is it a take activity? Is it a return activity? So as activity analysis. And as I showed you, you have multiple sensors. So you put all this information together to generate a receipt that is sensor fusion. So the difference between a textbook and the just walk out technology is that our algorithm must not just work statistically, but they need to be better than the state of the art. Okay. So let's go through some of the complexity here. Originally we thought we only need to locate the customer when they're shopping at the shelf. Turns out we didn't get the level of accuracy we needed, and we needed to locate the customer from store entry to exit. And if there's one customer, it's easy, but when there are lots of customers, then it becomes complex because of occlusion, and sometimes they may appear to be similar to each other. So that's the difficulty in there. So let me show you a view, a top-level view of the system in action. So what we have here is a bunch of disks. Each disk represents a identified person, and we put a label. The idea is we need to locate this this circle in every frame and persist the label. So the green label right here, such as D1 or E9, needs to be preserved during the sequence. So we have the entry right here, we have our shelves right here, we have shelves here, shelves there. So I'm gonna show you what is happening. I want you to specifically pay attention to this 1I7 label in particular. We'll also take a look at B6. So here it is. And you can see what, okay, the I-17 turned yellow. When it turns yellow is that we know the presence of the customer because we have no trapdoors and we have no teleportation. So we know, but we don't know precisely where it is. So we create what we call a tangled state there. Okay, so that's the example. Another difficulty here is that we have many products in our store. We have ready-to-eat foods, we have meal kits, we have beverages. Some are challenges because they are very similar to each other. So we solve this with a combination of categorization, which is essentially indexing, and deep networks for fine-grained recognition. So we can recognize thousands of products, and we are robust to illumination changes, shadows, reflection, which actually occur in the real world. So here are some examples of products that are very similar visually, but are different. So that's a Bombay potatoes and chana masala are very, very similar, but they are actually different. And on the right is instead the same product, which is looks very different due to lighting or movement. Okay, so now how do we solve the association between the product and the customer is done by, again, a deep learning. We find an articulated model, and here is a replay of an activity where we have replaced the actual customer actions by the interpretation from the system. So we see that that is what our system understands. Okay, so where are we today with this? Well, we have many stores. We have them in Seattle, San Francisco, Chicago, New York. We have also expanded internationally. We now have a full grocery store that is powered by JWO. And we created this Just Workout experience, which pushed the boundaries of computer vision, machine learning, and sensor fusion along the way. But essentially, we started with what is the customer problem? And the answer is not obviously just workout technology. This is where the quote makes sense. We take the problem, you invent on behalf of the customer, and you provide a customer experience which addresses this customer problem. So that was the first example. Let's take the second example, which is Amazon One, which was introduced late 2020. So again, what is the customer problem we're trying to solve here is that unlike in the online world where you can pay with a click or authenticate, in the physical world, this takes time and it adds friction. I mean, you need to go look for your credit card as this person is doing here, or you need to fish for your phone, and it creates friction. What we want to do here is give customers time back, and time is a very precious resource. So let's start with a quick video that explains the customer experience right here. So let's listen to Zoe.
This is Zoe. Just like you, she uses lots of different cards and IDs to get through her day. What if all Zoe needed was herself? Introducing Amazon One, a free service that lets you use your palm to quickly pay for things, gain access, earn rewards, and more. Let's say you're grabbing your favorite coffee beverage, or heading into the office, or checking out. Just hover your palm and you're on your way. It's as easy as that. Sign up is free and takes less than a minute. All you need is a credit card, your phone number, and your palm. That's it. Since your palm is unique and can't be lost or misplaced, you can get things done quickly and securely. And with more experiences on the way, Amazon One will help you get even more done, simply by being you. Now, Zoe has more time to do what she loves: indoor skydiving. Enter, identify, and pay with Amazon One.
What is the customer experience in there? Well, it is safe, it's easy, it's convenient to both to enter, to identify, to pay. First thing is that you're in control. Each time you use Amazon One, you intentionally need to put your hand over the device to scan your palm for it to work. So you get to decide exactly when and where to be recognized. The second one is no two palms are alike. It is a unique part of you. So it doesn't go anywhere. You don't, and it can't be used by anyone but you. And finally, it's a truly contactless interaction. Once you have signed up, you never have to touch anything to use it. So, what are the lessons here? The lesson is that if you listen to customers, you hear about pain points. You're not hearing of a solution. So again, if I tell you I hate waiting in line in the supermarket, it doesn't automatically translate into, oh, just walk out. Okay. So the invention part is to come up with JW. The same thing. If you say, well, it takes too long to authenticate, well, that doesn't translate immediately to Amazon One. This is where the invention is. Okay. So now to get there, to get from the notion of, oh, let's do it, let's invent, you need both dreamers and builders to go from the idea to the implementation and to turn invention into reality. And you have to be stubborn on the vision. You know what you want. You know what is the customer problem you have to solve. But you need to be flexible on the approach. You need to explore in order to get to the right solution. Well, that brings me to the end of my lecture here. The end of the journey, the current journey. And I want to close with these words right here that in terms of the computer vision, which is the area that I know the work I've been doing for 40+ years, it is a golden age. Why? It is because computer vision now works to solve real problems in commercial application. Computer vision is real. Second, it is a wonderful sandbox for science and engineering. And this relates to my comment about dreamers and builders. Science and engineering. You need to create the concept, you need to develop it, and then you need to make it into a product. And there are many, many opportunities. Many opportunities not for research, but startups. Lots of startups can leverage these advances in computer vision. And not just startups, but large companies that are making a significant investment in computer vision. And obviously Amazon, Google, Apple, Microsoft, Facebook, all of these companies are looking at computer vision as a core technology to reinvent the future. With that, I want to thank you for coming along on this journey through my career in the field of computer vision, and I hope you enjoyed it. Thank you very much.